All right, our last video for day one, block 4, we're going to start talking about proofs. So a major topic this geometry unit is proofs and proof writing. So we're just going to introduce a little bit here and talk about some specific terminology and theorems that you might need to know to get us started with writing proofs. Okay, so before we even get into any of that, I just want to tell you a quick story. Okay, so here's my story. You can follow along. I washed my face. I ate chicken and rice for dinner. I was driving home. I had goldfish as a snack. I listened to 101.9 radio. I fell asleep. I watched Adam Ruins Everything on Netflix. And I brushed my teeth. Now, when I tell that story, and I wanted to tell you about my night last night, that makes almost no sense. You can kind of piece it together, but it's really confusing. So what I want you to do is take a moment to number each statement above, so just write a number next to it, in an order that makes sense to you. Now, there's not necessarily one exact order here, but put it in an order that makes more sense than what I have. All right, so here's how I ordered the story. So instead of what I told you before, I was driving home. I listened to 101.9 radio. I had goldfish as a snack. Then I watched Adam Ruins Everything on Netflix. I ate chicken and rice for dinner. I brushed my teeth. I washed my face. And I fell asleep. Now that sequence makes a lot more sense. You can see how each step kind of leads into the next step. It does not make sense that I fell asleep before I even watched the TV show, right? So that's kind of the basis of proofs. Proof is basically an argument in which you list statements that you believe to be true and you provide justification. So that's the part we haven't quite touched on yet. We have to always give reasons. So, well, if you're saying that these two segments are congruent, how do you know? Okay, so we write mathematical proofs, but let's take a look at a simple one about this dog, just to kind of see how you can have the statement and then the justification or the reason. So number 1, it says Fifi is a Labradoodle. Therefore, Fifi is a dog because all Labradoodles are dogs. So that's our justification of how we know Fifi is a dog. Therefore, Fifi is a mammal because all dogs are mammals. Therefore, Fifi will never lay any eggs because mammals don't lay eggs. Okay, except for platypuses and spiny anteaters, for those of you that know more about that kind of stuff. But in general, mammals don't lay eggs. Therefore, Fifi will not lay any eggs on the 4th of July because if she'll never lay any eggs at all, she can't lay eggs on the 4th of July. So, in a nutshell, the Labradoodle is a dog, which is a mammal, which means no eggs, which means no eggs on July 4th. It's a domino effect. Each statement knocks over the other until you get to your final conclusion. I know logically, yeah, I could have said from the beginning, the Labradoodle is not going to be laying eggs on July 4th, but we need each statement in between to show the reasoning, the justification of how we got to this ultimate conclusion. Okay? So when we write mathematical proofs, we want to just remember some of our algebraic properties. Now, these are all the properties that you've used to solve equations, but we're just going to refresh our memory on kind of the names for them. So when we reference them in proofs, you have that in the back of your head. So our addition property, that's what allows us to solve equations, take steps in solving equations. So we're just going to fill in the example columns for all of these. So we can say if A equals B, then A plus 2 equals B plus 2. Right? This, you have the property written in all variables. We'll just do a quick example. Right? If you add the same thing to something that's already equal, it stays the same. Subtraction property. If A equals B, then A minus 2 equals B minus 2. Okay, that's what allows us to like subtract a variable from both sides to move it over, something like that. Multiplication, if A equals B, then A times 2 equals B times 2. Division property, if A equals B, then A divided by 2 equals B divided by 2. Pretty straightforward here. We have our substitution property. We'll use this one a little bit throughout our proofs. If A equals B and A equals 20, I'm just making up an example here, then B equals 20. I substituted 20 in place of A, right? Because 20 equals 20. Okay. And then our distributive property. A couple examples. We know our distributive property. 2 times x plus 4 becomes 2x plus 8. 2 times x minus 4 becomes 2x minus 8. We're familiar with that one. So just a couple of algebraic properties, because we actually, even though it's geometry, we use a ton of algebra here, so we do want to remember those properties, especially when we're using them in proofs. So in general, you have 3 formats for a proof. We use 2-column proofs in this class. That's our big focus. A 2-column proof is very structured, and it literally is made up of 2 columns, T-chart. On the left, you have all of your statements, and on the right, you have your reasons why that statement is true. So for example, from the dog example, we would say that Fifi is a dog, and the reason would be because all Labradoodles are dogs, right? So we'll practice this a bunch. That's how we write the proofs. Other ones that just are good to know, we don't write them in this class, is a flow chart. It's a little bit looser. You have statements, and then you have your reasons underneath that lead to more statements, kind of following the flow of the argument. And then a paragraph proof is a written explanation. If you go on to take a lot of math classes in college, you write mostly paragraph proofs, detailing your reasoning in a paragraph. So we're just going to look at a very, very simple 2-column proof. It can be a lot at first, so don't be stressed out if you're a little bit like overwhelmed. We're going to do a ton of practice, but just to give you an idea of where we're headed, a 2-column proof here. So we are given a statement. You'll always be given some information, and we're trying to prove a certain statement. So we're given that T is the midpoint. We'll talk more about midpoint, but it's exactly like it sounds. It means that T is in the middle of this line segment. This is U over here. And what that means is that these 2 sections are congruent. Don't worry about the reasoning, just look at the structure of it, the setup, what it looks like. I'm not expecting that you could fill all this in right now at all. We're just introducing it. So no stress if it's a little confusing. So when we're writing a proof, the very first thing we'll do every single time is rewrite whatever was given. Just copy it exactly. So you can see it's already done here. And the reason is always given. So we always, always, always start with this. So if anything else, you should at least get the first one right. Okay. And then the next, we'll use what we know about that given statement to write another statement. So if T is the midpoint, then we can say that these 2 sections are congruent. Don't worry about the geometry, we'll get into that, but this is the structure. The reason is the definition of a midpoint. If they're congruent, then they're equal because they're congruent segments. No big deal if you're a little confused there. So that means we can take their equations and set them equal. So this would be from our substitution property. We'll just write substitution for the reason, because ST is 7x. They're equal to each other. So I substituted ST for 7x and TU for 3x plus 20. And now, just naturally, what you'd want to do is probably start to solve this. So I have 4x equals 20. Now, how did I get there? We used our subtraction property, right? I subtracted 3x. And then lastly, I ended up with x equals 5. How did we get there? That's our division property. Again, I'm not expecting that you followed every single thing I just said or that you could reproduce this. Just look at the setup, right? You can see each statement matches with a reason, things like that, how it kind of flows logically. We'll do a lot of practice. And the last thing that we need to talk about today is some properties of equality. Lots of stuff on here. I'm just going to point out what you need to take away from all of this text. Our reflexive property, we use a ton. We'll use it a lot later in the second week of this course, but it just says that something is equal to itself, right? So the number A equals A. Segment AB is congruent to segment AB. This one we use a lot. Angle A is congruent to angle A. I know it seems silly, but you need to state everything so clearly in the proof that it's obvious and clear what you're arguing and how you know. So we will actually say things a lot, that AB is congruent to AB. It seems like, yeah, duh, of course it is, but we still need to say that, and our reason here would be the reflexive property. The symmetric property, we don't use quite as much, but it's still worth knowing. That just means you can flip the order around the equal sign, right? If A equals B, then B equals A. And then our transitive property, we use that one a lot. We've already talked about this. If A equals B and B equals C, then A equals C. Here's a good example with segments. We might use it more with segments and angles in this class. Here's an example with angles. This one has a bit of a typo. This should just say angle A is congruent to angle C at the end. If A is congruent to B, B is congruent to C, then A is congruent to C. Okay, so these two, reflexive and transitive, we'll use a lot in our proof writing. This set of notes, I might keep this, like save this somewhere that you can easily access it, maybe the same place you have your conditional statement list, because it has a lot of this vocabulary that's helpful for writing proofs. It has a good example of a proof and like all of our algebraic properties. So you might want this one kind of handy as well as we move forward in the rest of the geometry unit.